I think it has started. Okay. Now, let us derive the equation for stresses in case of unsymmetrical bending. Before I start doing that, we will take a cross section. Let us say, can we draw here? Yes, I will. Let's say, oh, here it is there already. Yeah? The unsymmetrical bending, this is y and z, and this is not symmetrical about any of the axes, and let's say it is subjected to bending moment in this direction. Okay. Now this is the moment axis, and perpendicular to that I have drawn one more axis. I hope let us try to make it slightly bigger. Okay. Here you can see this section, which is we have got two axes z and y. The section is not symmetrical about any of the axes. Now let us say the moment is applied in this direction. Now this is the moment axis I have projected. I have called that as z prime, and we know that this is the y prime. Now the question is, let us say we want to know which ink is this ink maybe. So let us say we have to answer the question in which plane the beam will bend. Beam will bend. Then where is the neutral axis position? We have to answer these two questions. If we can answer these two questions, then calculating sigma xx or sigma yy is not very difficult actually, or sigma. So those things are not difficult, or sigma zz, whatever is depending upon the moment, what stresses will develop, we will find out. Okay. Now, which plane the beam will bend? In which plane the beam will bend? Beam. Oh, it has become something else. Beam will bend. Now, before answering this question, let me put one more slide here. New slide, I think. Layout should be like this. Okay. Now, before answering this question, let me do one thing. We will revisit our simple bending. In case of symmetrical bending, where is the neutral axis position, we'll find out. Okay. Now, if you take I will try to draw a three-dimensional view so that you will appreciate it better. I will not show supports. This is the beam. Let's say our axes are like this. We will take a different ink and we will say that all this ink will be better, I think. This is X and the vertically downwards. This we will call it Y and this we will call it Z. Okay. This is X, Y, Z and we said that neutral surface will be something like this. This is the neutral surface. So let's say our this is mz, we will call this is again mz by equilibrium. So what will happen in case of let us say symmetrical bending, because we have an axis of symmetry. So in case of symmetrical bending, the neutral surface neutral surface will be in this which is plane actually. It is in xz plane. You agree or not?
Yes,
It is in xz plane, is perpendicular to the loading plane. The loading plane here is xy. Okay, the loading plane is the xy. So this is what in our symmetrical bending. Now we should find out what would be the thing for the unsymmetrical bending. We will assume that this is the same thing, it has blown and shown in 2D condition. So what we will do here, we will make a very simple assumptions that the moment is in this direction. I take component of moment along y and z axis. The moment which was not in previously, let's see where is it, can we see? The moment which was not in either y direction or z direction. To simplify our analysis, what we did, what let us do is, we will take m along the component of m along y axis and component of m along z axis we will take. So that will help because of our analysis. The analysis becomes slightly simple actually. So that's what we will do. Not the principal in such cases resolve the applied moment vector into my and amz. So to help our analysis, it doesn't matter. You may, what happened? You have to wait. Okay. So now let us say simple bending neutral axis is in XZ plane and the loading plane is XY. That's what we said. What will happen is along exit plane you have the moment, your neutral surface, neutral axis and the CG coincide. That all we all know. Up to this it is fine. Now we will assume that the assumptions we made in case of simple bending, that is the plane sections which are perpendicular to the centroidal axis and the plane sections which were plane before bending and perpendicular to the new centroidal axis, that is centroidal axis means CG axis, will remain the plane and perpendicular to the centroidal axis even after bending. Okay, that is what we made an assumption in case of simple bending. I believe it is easy. Where is it? I don't know. Simple bending is not even coming. Forget about the assumption. The cross sections normal to the centroidal axis of the beam before bending will remain perpendicular to the centroidal axis. Slightly let us make it bigger. Okay, then beam before bending will remain perpendicular to the centroidal axis after bending. Then that is what we have made assumption, and material is homogeneous isotropy. We have discussed what is isotropy, what is a homogeneous. Then fiber along the centroidal, along the neutral axis remain unstretched. In this case, it is centroidal axis, but in our case, it is in the unsymmetrical bending. It remains what do you call as a neutral axis. So let us see whether. Okay, now we have come very good. Oh, these assumptions is given here also, unfortunate. So these assumptions we will they are valid in case of unsymmetrical bending also. The whatever the assumptions we made in case of simple bending, they remain valid in case of unsymmetrical bending. As I said, the story is the same. Unsymmetrical bending was also solved initially by mathematicians. They wanted to make the problem simple in the sense the underlying, you see, whenever we are given a physical problem like bending of a beam, then what they want is they want a mathematical model for that. Mathematical model is the differential equation. That is, all of. I don't know whether you must be knowing that how do you find out deflection? EI d square y by dx square, where y is the deformation. In our case, I think it is v. EI d square v by dx square, because that is the curvature. EI into curvature will be equal to applied moment. That is what they derive. But they could derive those equations based on these assumptions. Those equations were very simple to solve and they were very happy. Similarly, these assumptions were made. These assumptions were made based on all these assumptions are made based on some experimental evidence. And nowadays, with sophisticated experimental equipment, these assumptions are verified to a great extent. In the sense, even to whether they are exactly perpendicular or not, everything has been verified actually. Okay. So you don't have to worry about these assumptions, they are valid actually. You may think that they may not be valid in the case of unsymmetrical bending. All these things have been verified. You can also do these things in our lab actually because we have also got that very sophisticated equipment. So, and okay, now what we know is neutral axis, let's say we passes through, let us say, we have shown here it is passing through centroidal axis directly. We can do from here, there is no problem. Let us assume neutral axis passing through centroidal axis. If it doesn't pass through centroidal axis, then we will get some value for these things will not be valid, and or you can do other thing in the sense we will do one more thing. We will introduce, insert a new slide. Where is the pen? This is Y and Z. Okay. Now let us say we have applied some moment. I am not worried about those moments. I am not showing. Let's say I will assume some neutral axis somewhere here. Just for the sake of that, consider a small area. From the assumptions, it is very clear that strain at any point at a distance r from the neutral axis, that is perpendicular distance from the neutral axis, will be given by, let us say, epsilon xx is r by r and sigma xx is equal to E into r by r. Okay. Now, now we have to have by, let us say we have not applied any axial force. So sigma nxx should be equal to 0 or sigma fx is equal to 0. In this direction it is positive because x positive direction is this one. Now this is nothing but sigma xx dA should be equal to 0. Area integral, then this will be E by R integral R dA. This will be equal to 0. E by R into R bar area equal to 0. So E by R will go that side and A is also not equal to 0. So What is 0 is this one. So the neutral axis passes through from the CG of that. So, but that again I will show you in the previous class, in this slide also we will see that. Now from these assumptions, what will happen is the strain will vary linearly from the neutral axis. Okay. The assumptions, what we have made, that as a consequence of the assumption, the top fibers get compressed and the bottom fibers get stretched, and there is a fiber in between the top and the bottom fibers which were neither stretched nor compressed. And if you take the neutral axis along that line, now the strain at any point, because they have to remain perpendicular, the strain will linearly vary from the neutral axis. That is what the assumptions will tell you actually. Now based on that, that is R by R. R by R we have derived in our simple bending because at any fiber the length will increase by, that is the strain is R by R or Y by R we have derived. I think if you want, if you have already forgotten, this is which slide is this? This is 80, okay. I can show you, but unnecessarily it takes extra time to draw. Okay. Here we have shown that epsilon is equal to Y by R. Strain at any location is Y by R. So because of our assumptions, the plane sections remain plane and perpendicular. What will happen is top fibers get compressed and the bottom fiber gets stretched, and there is a line here which neither gets stretched or compressed. And at these points the strain is Y by R. Y I have taken as a distance. Now we have gone to 80, let us say 80, 80, 80. Okay. Now here instead of Y I have taken R. This is the neutral axis position. So at any location, let us say N. Let us take this as a N. So let us say it makes an R, this is the distance ND prime. So ND prime, it is the distance. As you move away, R becomes larger and larger, the strain will become larger and larger. Now you know Hooke's law, you know that the stress is nothing but strain multiplied by the Young's modulus. So that is what we have written. E R by R, 1 by R is usually known as the curvature, that is denoted by kappa. Then now from geometry, R may be written as, let's say we make some construction, you draw a, let's say this neutral axis we will assume makes an angle beta with respect to Y axis. If beta it doesn't make beta, it makes 0, then we know along which side the neutral axis lies. Let us assume that it makes an angle beta. Okay, now fine. Now let us make a you prolong this and draw a line perpendicular to this line parallel to the neutral axis. So it will go and join the Z axis at P, and from this you draw the vertical plane. Then N in this coordinates are Y comma Z. Y is this distance is y. So we know what is the y distance, and then we will make. So let us say what is the r. R is nothing but nd minus d dash d, that will be equal to nd will be equal to, this is also sine beta, this is y, so y sine beta minus z cos beta. So up to that there is no doubt. Now uh, substituting the value in the r bending stress expression is e kappa y sine beta minus z. This is, let us say, what is this? I think it should be, I think I'll draw one figure so that you will appreciate it better actually. Mm, uh, is there a space in the next figure? Or, mm, here itself we can draw, no problem. See, we here it is said um, k sine beta. Where is the pen I said? K sine beta is the projected curvature in the xy plane. What is that? We will write K sine beta, that is kappa sine beta. Let's erase this. This is of no use. Kappa sine beta, they say, as the projected curvature in the xy plane. What is that you want? Let's say you write that projected curvature in xy. What does it mean actually? Let us see that x, y, okay, maybe z, maybe like this. Now let's say we apply bending moment is positive in this direction, and the positive curvature will be this. Curvature is the, this is what we measure. So positive curvature will be this. So you measure, this is the radius of curvature, then 1 by r is what is the curvature in the case. So that's why it is known as, I think, KZZ. Uh, K, it is K, oh sorry, it is in the, along the Y, so it is usually known as kappa Y. Then K sine beta or kappa cos beta, sorry. Kappa cos beta projected curvature in exact plane. So it is naturally known as concepts. Okay. Now, how do you represent that? This you will represent it by, let us see, X, Z, actually, and I think X, Z, I think Y will be along this very fast. Now the positive bending moment direction will be like this. The positive curvature direction will be this. So I just want to have a picture of all those things. These are positive bending moment, and this is the positive curvature. But whatever we get, we will get. Whether it is positive or negative, it hardly matters to us.
Sir,
Yes.
can you once again explain this KYY?
You see, uh, you see, let's say you have a curve. Okay, take 2 points, draw perpendicular in the sense you will join this radius vector. They will join, and that origin it will go and join. Let's say it's a circular arc of a circle, then you draw the radius vector, they will go and they join. Now this we call this as radius of curvature. Is it agreed?
Yes, sir.
Now the 1 by r is there. This is radius of curvature, and this is only known as curvature actually. Okay.
Yes, sir.
Now actually, because in an unsymmetrical bending, you see in usual problem what will happen, the loading in xy plane, in symmetrical bending, let us I will show you in red what is there in symmetrical bending. You will have x, you will have y, so the loading is in xy plane. Either it will bend like this or it will bend like this. Okay, so depending upon bending, the curvature sign will change, because our radius, if you join this side, it will become r will become positive, and if you join this side, it will become negative. Okay,
Okay, sir.
so that is what I was trying. Whether the bending is in xy plane, or, but in our case we will have bending in xy plane as well as bending in xz plane. Why is that? Because I have changed. I have where is our? I have moment is in this one. It will bend in some plane. But to find out that, I have taken the component along z-axis, component along the y-axis. So it will we will have curvature along y-axis and the curvature along z-axis. Okay.
Okay, sir. Got it.
Now we will go ahead from Hooke's law. We know what is sigma xx. This is r into e kappa. Then r we said we will differ this one. So sigma xx is equal to e kappa y sine beta minus z kappa. So this is they call as some projected curvature in xz plane, and this one. So we will have y has come, y, okay, so y was the original coordinate. Okay, this is the thing we will have. Now we have introduced now let us say sigma xx dA, then e kappa r dA, then it will what will happen? Okay, then this will give r bar equal to 0. because these things are all non-zero quantity. Area is a non-zero quantity, so naturally R bar should be 0. What does it mean? R bar 0 means what? Then our neutral plane passes through the CG actually. R bar 0 means our neutral plane passes through CG. Why is that? Because at the neutral plane, I should not have any sigma xx, isn't it? Because the neutral plane is the plane where I should not have either stretching or compression. That means the sigma xx should be absent. So for that sigma xx to be absent, R bar 0. So naturally my neutral axis passes through the CG actually. What I have chosen is perfectly all right actually. Okay. Now we have got I think sigma xx is this. Then I have written m is equal to my is equal to the z into, let us say, mz. You will have moment about z axis, that is y sigma xx dA. Then this is z sigma xx dA. So if you multiply, okay, we will do that in a longhand. I think we will do here my integral z into sigma x. Sigma xx is what? E into y cup of y minus z x into d. Is equal to area. E I take it outside because it is constant. Yz kappa y1 dA minus E z square upon zz d. These things constant, you can take it out. So integral yz dA is what? Iyz minus E kappa zz, you can take it out, so it will be not there. Integral area z square dA is the Iy. Okay, that is what it is written here. Is that okay?
Yes, sir.
If there is any doubt, you stop me and we will discuss this point again. You can longhand, you can do Ky is not a function of area. So dA, so naturally the out of this integral I have taken E as well as kappa yy. So I will be left with only function of yz dA. So yz dA by definition it is Iyz. Okay. Now, similarly, if I do in the longhand, let us do it. What is that? Shall I erase this?
Yes, sir.
No, no problem. Okay. So let's do my we did. Nah? We will do mz. Y. let me do this. E kappa y1 area integral area integral, let us say y square dA minus E kappa zz into yz dA. Then this will be E kappa y square by definition is izz minus ekzz into iy. There are no 2-3 steps has been removed, and that's why it looks odd actually. So now what they have done is solving for E by y and ekz. So for that, we can do here. Okay, I think it's not very clear. Let us put one more slide. Yes, now let's say the slide home layout will be blank. Oh. Now what we got, sigma my equal to oh. My is equal to ekyy. Acha. We copy this. Oh. Anyhow, doesn't matter. So let us write that my is equal to E kappa y izz minus ekzz I. This is, and then mz will be equal to E k izz minus ekzz kappa zz I. Okay? I think these two things are not required. How to remove this? Delete it there. I don't know. Cut it there. So we have got our equations. Okay, now what they want is they want to write this as equations. So let us say my mz then iyz iyz and this will be e kappa 1 and minus 2 kappa. So you can now solve for e kappa yy and e kappa z. I hope now it is all right. There, I think I will not solve. You will have to take the determinant, divide, and you interchange this and sign changes. All those things. It is a 2 by 2. So where are we actually? I hope somewhere it is there. Here we have got already. The same thing we have got. Okay, now stress is what? Stress is E into R by R. Here R by R has become slightly complicated in this one because sigma x is this one. Okay, now we will have E y k y y minus z k z z. We will have sigma x. So if you know what is my, you know what is mz. So these things you will have to substitute in our stress equation sigma x. Your stress equation, you substitute that EKYY and EKZZ. That means let me write down here so that I can write there very sigma XX is equal to EY kappa YY minus Z E kappa. Okay. Now you find out these things. Already somebody has done it. I have done it previously. So you take it for granted. You invert that and get this. Is that all right?
Yes, sir.
And now once I know EKYY, EKZZ, I will I know EKYY. EKYY and minus EKZ.
Sir.
Yes. 1 second. Let me write this. Y into EKYY plus Z into minus EK. So what you have to do is, once again, I'll come back to your question, whatever your question may be. Now I have written EKYY is MZ IYY minus MY IYZ divided by this denominator. Minus EKZ is the second row. MYIZZ minus MZ IYZ divided by this one. Okay. Now, if I do that, that Y into that stress is given by Y into EKYY. Y into EKYY you substitute, and Z into EKZZ you substitute. Because minus EKZZ I am substituting, so I am putting here as this. This is actually my stress equation. If you want to find out neutral plane, sigma xx along the neutral surface is 0 is known to us. So equate this equal to 0. So you will get tan beta is equal to z by I, y, that will be equal to this by this. Okay. So actually you don't have to do this, in the sense here we have got a tan beta, then you will have at this point, let us say tan beta is equal to what? Adjacent side by the opposite side by the adjacent side, opposite side being this ND, then this being PD, then you substitute that is nothing but y by z, because these are the coordinates of this point. So these are the z by y is nothing but the tan beta, that will give you this, or you don't want to find out this, that is nothing but there is another way of representing sigma xx. Wherever you want, you can represent this stresses, or you remember this equation, that is also fine. This equation is enough for all your practical purpose. But also you may have to find out neutral plane, then you have to find out what is let us say this, that side you take it out, this will you take it out this side, then we will calculate z by y is equal to this by this. Then you have located z by y is equal to this. You have located the you have located the tan bit. Okay, so up to this everything is fine. Now there were some questions. Let me ask. What is that?
Sir, what is difference between KZZ and simple K?
Huh?
What
K?
is the difference between ZZ and simple K?
Acha. See, simple K will not tell you in which plane it is bending. In symmetrical bending, we were representing it by K. We knew that as soon as the loading plane is XY, it will also bend in the XY plane, because it was simple bending, isn't it? So that's why we didn't bother to put KYY. That is why we didn't want to put. It is actually KYY in simple bending. But since it bends in both ways, in the sense Let me, whether I don't know whether I am visible or not. Let's take this as a beam. Okay. Now in simple bending, it will bend like this. Okay. So it is actually KYY. Okay. If you draw project and it will be R and 1 by R is what you are looking at. Okay. But in unsymmetrical bending, it will bend all about this and it will bend like this also. In the sense, it doesn't look like I can bend both ways, this one. See, this way it will bend and sideways also it will bend. I can't bend this. Let's see. There is one page I will take up. Show you. No. This way. You see, it will bend about because M we have taken out about Z axis, also about Y axis. So naturally it will bend sideways, isn't it? And also it will bend this one. I will, I think maybe better to show it to you by I think here if I can show, let's see. You see, this is my axis. This is Y axis. This is Z axis. Let's say. This is, I think, Z axis. This is Y axis. Let's say my moment is in this direction. So what I did was I will take moment about Z axis, MZ, and moment along Y axis. About Y axis, you see this will like this, so it will bend about Y axis like this. Okay, that is in XY plane. Now, because of Z axis, the moment is about Z axis in this plane. So, it will be bending like this. It will be bending like this. Okay, it will bend about both the axes. The sum of both will actually the bending plane. That's why neutral axis is inclined. You follow?
Yes, sir.
Because the M is not about any one of the axes. M is general direction, so naturally double arrow. Okay. Now, but what I did was to simplify my analysis, I taken the component along Y axis and component along Z axis. So about Z axis, how it will bend, you know. Let's say for simple bending, you take it. Let's say this is X, this is Y, and this is Z axis. Okay. Now, if you have moment like this, the beam will bend like this. If I want to show in only one line. Okay, because the beam. Now this M by Y also tries to bend in one direction. MZZ tries to bend in another direction. That's why my neutral axis is inclined actually. That's why we calculate beta. Okay, I think tomorrow, no, tomorrow we don't have class, is it? No. Then Monday I will try to solve problems. During that time I will try to explain as much as possible so that you better understand. Let us see. I hope if you have doubts, you can all ask on Monday. I think it is 11:05. I think I should not encroach on somebody's